Good afternoon, everyone. Our project is entitled 3D Self-Supervised Methods for Medical Data Efficiency. And let's turn into the problem statement directly. So what is the problem? The problem is that the key requirement for the success of supervised deep learning is a large labeled data set, a condition that is difficult to meet in medical image analysis. Annotation of 3D medical images like CT and MRI is a challenging, time-consuming, and expensive task that can be performed only by qualified doctors. One image requires about from 20 to 30 minutes of time. And what do we want? We want to obtain models with higher quality despite the small amount of labeled data. And how can we reach this purpose? The answer is self-supervised learning. It provides a strategy to pre-train a neural network with unlabeled data, followed by fine-tuning for a downstream task with limited annotations. And there are many types of self-supervised methods, but we will discuss only the types that directly correspond to our work. And there are self-prediction methods like image rotation or jigsaw puzzle solving, and the second is contrastive learning. For example, imagine that if you have image of monkey and you have augmented image that you can see in the picture in the slide, we generate an embedding for original image and embedding for augmented image, and we want to enforce that neural network will have a similar embedding for two of these two images, and we'll have dissimilar embedding for monkey and tiger. And another interesting approach is pixel-wise contrastive learning. In this case, we generate embedding not for whole image, but for each pixel of the image. Now, Farooq will tell you about data.
Thank you, Kijik. Let's talk a little bit about data. We use a pancreas tumor dataset, which consists of 420 3D CT images on which the pancreas with tumors is present. The data annotation represents as binary segmentation mask of the pancreas and segmentation mask tumor. Why is the task of early diagnosis of pancreas tumor so important? First, it was starting with the fact that most pancreas tumors are cancer, and pancreatic cancer is extremely dangerous disease. And on the slide, you can see facts confirming my words. Okay, now let's go back to our main task, self-supervised learning, and talk about the method that we use in details. The first and simple method of pre-training that we use it is 3D rotation. To do this, we rotate input image by 10 random angles, and we use only encoder part of UNet to solve the problem of classifying the angle of rotation of the original image. The second method is jigsaw puzzle solving. In this method, we split the image into 27 patches and made a permutation of these patches. Along all possible permutation, we choose only 1,000 different, and and then using the encoder part of backbone, we try to predict the class that correspond to the permutation. Cross entropy use it as loss in both cases. Now Vera will tell us about more interesting approach.
Let's look at pixel-wise contrastive learning. Since we are solving segmentation task, which is pixel-wise classification, it would be interesting to get embedding of pixel-wise embedding, not embedding for the whole image. How it works? Imagine we have an input, and we apply to this input two different transforms, T1 and T2. Then we pass it through a 3D UNet with the projection head and get three outputs: output, output 1, and output 2. Then we apply transform T1 to the output, which is the result of applying of our model to the input. And we get this one. every voxel in this image has a vector of line 8 correspond to every voxel to these images. So we want the voxel features with same spatial coordinates to be positive pairs in T1 to output and output 1, while the voxel features with same spatial coordinates of output 1 and output 2, we want to be negative pairs. The loss that we use is presented on the slide. Here you can see that every pixel of the output 1 has one positive pair and one negative pair. Then this loss is averaged along all the voxels. What transformed we use? We use random rotation, random shift, random scale, and the transform that didn't used in previous papers is elastic deformation. Here you can see original image and the result of applying only elastic deformation, just to see how it looks. And here you can see an example of all random transforms applied to the original image. Here you can see the feature maps that our model learned. We have several original image and the feature maps for them, and transformed image with feature maps for transformed images. As you can see, there is an equivariance between these two feature maps, and pixels with the same spatial coordinates really correspond to the same, to close features. How we fine-tuned our model. For 3D jigsaw puzzle and 3D rotation, we uploaded weights of our encoder to the 3D UNet, and then the first 80 epochs of the model were trained with frozen encoder weights, and then the whole model were trained. In pixel-wise self-supervised learning, we uploaded the weights of 3D UNet and then added a new projection head. First, 8 epochs only new projection head were training, and then we trained the whole model together. We fine-tuned our models on different amount of training data, 10, 25, 80, and 100% of training data set. And our baseline with which we were compared was 3D UNet trained from scratch.
So in the slide, we can see our results of our project. This plot is quite interesting. First, we can notice that all our methods with pre-training and self-supervised methods demonstrate better quality in case of tumor segmentation, but baseline, its UNet, is better from the point of view of die-score in the case of pancreas segmentation. It can be noticed that already for a small fraction of data sets, all our nets demonstrate a low quality in case of tumor segmentation, but quite high score in pancreas segmentation. Due to this fact, we can provide some kind of explanation of this phenomenon. It can be occurred because tumor segmentation is a more complex task for nets, and every additional information from pre-trained nets, from self-supervised methods is very useful. But it's more than enough for pancreas segmentation. And in this case, baseline demonstrate better results due to this fact. Thankfully, our scores is not so high. It's normal. We provide a competition winner results and a UNet, and this score is also not so high. It's comparable, absolutely comparable with our results. Of course, in ideal situation, we should train our network with different initializations and different times to obtain more statistical representative results, but we haven't so much time and computational resources. In conclusion, again, all the pre-trained methods improve tumor segmentation, but preferred methods worsen pancreas segmentation because tumor is a much more complicated task. So that's all. Thank you for your attention.